Hello. So we are starting with uh, today's PCD of CodeChef. So this was the first problem of day 4. Uh, the problem is exercise and rest. The chef is on a new exercise plan. He will work out for 2 days, then take 1 day rest, and then repeat. Today is chef's NIT rest day. How many days, including today, has it has it been since chef started his plan? So this is an simple question. Means in the input we have to give there is given an n and we have to say how many days it took. So like if there is there is a chef, he takes 2 days work and 1 day rest, 1 day rest, and he will take rest only after working 2 days. He will take rest only after working 2 days. So means there will be rest, work, rest. So this will be in this pattern. So if this is the second day of rest, second day of rest, second day of rest. So for this, you can see first group 3 days, then second day of rest 3 days. Like this in same manner, 3 days, 3 days it will come. So if there is any, he's taking any day rest. So we can directly say that by seeing this formula, he takes one rest day means he has almost working 3 days for that. So 3 days into n rest days, n n. So you can see the code here. The code is uh, just I'm taking the input and then I'm just printing C out n into 3. Okay, so I'll move on to the next program. This is Chococut. Okay. So Alice has a rectangular bar of chocolate dimension n cross m. This bar is made of n into m small square pieces. Unfortunately, Alice has to share the chocolate with Bob. At most one, at most once, Alice can break the mm, rectangular bar into a smaller rectangle either by making a vertical cut or a horizontal cut. The the two smaller curves must be have a integer dimension means they must have an integer dimension. Note that Alice can also choose to not break the bar at all. Here means here in the question it is said at most once means 0 or 1. So if it is not breaking means there is zero cuts. So Bob won't be happy unless he receives at least k of the 1 to 1 squares of chocolate. What is the largest number of squares of chocolate Alice can keep with her while ensuring Bob is happy with what he receives? So in this input format, we are giving three test cases where we give where the each test case contains n, m, and k, where n and m are the the chocolate's dimension, and k is the number of squares, 1 cross 1 square that Bob requires. So this question can be explained such that see here is an chocolate. This is a chocolate. Okay, so this is some this some pattern is there. This is the grid n cross n grid. So we can make a cut like this. We can make either make a cut like this, either make a cut like this or like this. This is an horizontal cut. Horizontal cut. This is a vertical cut. So miss in the question it is said miss there can be two types of cut, either a horizontal cut or a vertical cut. So we want we want to maximize Alice number of chocolates. Okay. We want to maximize this. So, what intention you can have that you're cutting this part, then giving it to this. Then, if Bob is not satisfied, then you are again cutting this part. If Bob is again not satisfied, you are cutting this part. If Bob is not satisfied, you are cutting this part. And this until we make the cuts, till Bob is satisfied. And we know Bob will be satisfied at once or a while because K is in this range is between n into m. So one is if total number of chocolates, if he gives the total chocolate, then also Bob is satisfied. So there will be one condition when Bob will be satisfied. There will be no condition that says that Bob is not satisfied. And so we can just try to do this, cut like this, like this, like this, and see how many remaining chocolate pieces are there in this part. Or else we can also do this that we can make this cut, we can give Bob this part, this part, this part, and this part, and we will see how much remaining chocolate left for Alice, and we will take the maximum of both the parts. So this was my logic for this second part. So let's move on to the code. So here I'm taking three test cases, and there I'm calling the solve function. Then I'm just taking the inputs, means n and m, the means dimension on the grid,
Bhaiya,
and k is
screen
the
is
number.
visible.
Huh?
Their screen is
No.
visible. At first, it was not visible.
Which screen? This screen.
Yes, Bhaiya.
Now it is visible.
Yes, Bhaiya. Yes, Bhaiya.
So, uh, uh, so here I'm just taking this k, dummy k. So I'm checking, means if Bob is satisfied, means how many chocolates are there, means total number of one square one pieces are n into m. And then I'm just cutting n pieces one by one, and I'm checking, means how many pieces will Bob get if there is an, means if every cut is n times, means n cross m. So this is an vertical cut, I think so. This is a vertical cut, and this is a horizontal cut. So these two are there. So this is the vertical cut, this is the horizontal cut, and whatever is the max means we are taking maximum of both of the means numbers. Means like in this case, I mean, first I thought to take just the minimum one, but I got an error. So which case was this? This was the case 9, 7, 23. Means if you take 7 only, then the answer is coming 35. But when you take 9, the answer is coming 36. So that's why I had to take both the cases. Means yeah, the greedy logic did not work. This is a brute force logic, you can say. So I will move on to the next question.
Bhaiya, in the previous question, if the constants were large, then we could use binary search now.
Binary search. Yeah, yeah, you can use.
Yes, Bhaiya. Okay, Bhaiya.
So, incremental game. Alice and Bob found two piles of stones, one with X stones and one other with Y stones. They decided to play a game using these piles. Alice and Bob are always trying to one up each other, so they decided to play under the following rules. The player takes turn moving with Alice going first. On Alice moving first, she must choose one of the piles and remove at least one and at first keystones. Thereafter, each player will choose one of the two piles and has to remove strictly more stones from it than the opponent previous move removed. If you are unable to do so, they will lose. For instance, if Alice moves three stones in the first move, Bob removes more than three stones in the next move, or else he will lose. There is no chemist in the no. There is no upper bound that the stones tell except for Alice on the first move. Means only in the first move there is a upper bound. Otherwise there is no upper bound for the next cases. Okay. Whichever player is who is unable to make a move loses. Okay. So here we are giving the input is like t test cases and then x, y, k, where x is the x is the in one pile y is number of stones, y is the y in one other pile number of stones, and k is the L on the first row. L is how many stones can be removed, maximum stones can be removed. This is the okay. So 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 this question was like this. Here are x stones, here are y stones. Okay, y pile. Okay, so here are two players, Alice and Bob. Alice and Bob. So what only first player has the constant to remove the stones. So what do you feel? So Alice can do from 1 to k. Okay, 1 to k. Suppose k is less than, suppose for this case k is less than x comma y. K is less than x comma y. Okay. So Alex is removing what Alex can remove? He can remove one stone, two stone, three stone, dot dot dot, two k stones means any one number of stones. Okay, from any one of the means this piles. So if Alice wants to remove here from here number of stones, suppose z stones. So here will be x minus z and here will y. Okay, so in next move, Bob has to pick more than x minus z. Bob has to pick Bob has to pick x minus z stones, more than x minus z stones. So here will be less than x minus z stones. Means here can be x minus z or more than x minus z. We cannot, but he has to pick. So he can pick the maximum stones also. Means what is the optimal strategy for Bob? He want to pick the maximum stones so that that Alice has no other way to miss beat him again. So Ali, for there is some stones, here is some stones. So Alice will always, Bob is always pick the maximum of the both the stones. So if this is maximum or this is maximum, he will pick that one. And in next opportunity, means in the next turn, Alice has to pick more than that. But there are no stones left. There are no stones left, so how will you pick? So obviously there is no optimal strategy for this is not an optimal strategy for Alice. So Alice has to pick always the maximum stone he can pick. Alice has to pick up max stones available for him. Available. Okay. So suppose Alice there is K. K K can be greater than x comma y. K can be between x comma y. K can be anything. Okay. K can be less than x comma y. So suppose there is a k. So either he will take the maximum of both the stones or he will take k. Okay. Means there is a maximum max of x comma y. This is the maximum number of stones he can pick. Okay. But he can here also the constant that k. Okay. So he can pick this much stones at first instance. Okay. So here let him pick. Alice can pick this much stone. Let Alice pick this much stone. Okay. Alice has picked. So Bob has to pick greater than what Alice has picked, not equals to also. Bob has to pick what Alice has picked more than that. So, so if there is more stones available than that, means if there are means whatever the stones remain, means suppose this was something and this was something, and from one pile we have cut it out. Okay, so one pi, suppose this was something, this was something, some Alice was, this was some value AZ. So some value I have to cut it out from the maximum, and then this was the minimum, this is the minimum. So if this part and this part is greater than the part we have to cut out, so then it is sure that Bob will win because there will be no other part left that is greater than that. Means if this part is greater, means this will be always smaller than that. Then how will Alice pick up anything? So it is not possible for Alice to pick up. So this is the optimal strategy that Whatever the maximum score Alice will pick. If Bob has an opportunity to pick more than that, then Bob will win or else Alice will win. This was a greedy solution. So let's see the implementation. So here I'm taking t square, then I'm calling the solve function. Here in the solve function, here in the solve function, this is the x here x is greater than equal to y always. Okay, this statement means this. Then I'm taking from the maximum tower. I'm cutting out the maximum number of stones that can be taken out for Alice. This is yes, Alice is taking these stones. Alice is taking these stones. Okay, so this is the number of stones taken. And if what I said this that Bob next opportunities for Bob. So if Bob can take this much stones, means if there are available, means if the total number of stones taken is more than what Bob is taken. So it is obviously Bob will take more. Bob will be the winner, or else there is no more stones left. So Alice is the winner. This was a simple solution. Uh, okay, so now yes, we'll continue from here.
Okay, am I audible?
Yes.
I hope my screen is visible. So let's start with the second question of the div 2, which is or what. What this question is basically asking you is to find a permutation. What is a permutation? It's a combination of numbers from 1 to natural numbers from 1 to n. Okay, so if you make a combination of that, that's a permutation of size n. So you have to make a permutation such that if you perform the OR operator with its index 1 base, by the way, this index is 1 base. Okay, so if we perform the OR operation with the index and the index and the number, it results in the x that will be given to you by the question itself. So you have to maximize this. And if there are multiple such permutations, you can output any of them. So how do we do this question? So obviously, what does an OR operator do? It basically combines the two bits of the bits of the two numbers, right? So if, for example, let's say I, the index, as a bit which is not present in X. If it is not present in X, then obviously we can't take I because there is no way to get rid of that bit, right? Let me just give an example, just in case. 1001, for example, there is no way to get rid of this one, right? You can do OR operator with anything. If you are only doing OR operator, of course, then there is no way to get rid of it. You can do this OR operator on any number. You can't get rid of it. So our first criteria would be to make sure that I has only those bits that are present in X. Okay. So that is what we have done. We are just iterating over the entire vector or the entire what do you call permutation. At first, I have not created a permutation. I'm just iterating to every number that we are going to have in the final permutation. So this is the condition. Of course, if X or I mean, all the bits, our first condition was I should have all the bits, X should have all the bits that are present in I, right? So if X or I, we do this operation, then it should be equal to X. So that is what we have essentially checked here. By this condition, we can validate, okay, I has only those bits that are present on X. There's no extra bits. After that, now our task is to make it equal to X, right? So what number we will need? That is the question, right? What is the number such that I can, let's say, convert this into convert this to 11001, let's say. Okay. So what is the most minimum number or the best option that we have, right? Of course, we can have extra bits. We can have, let's set that better. So we can have this number, right? This will be our best option. If we do OR operator this and this, it will give us this only 1101, right? So that is our target. Of course, we can have a 1 here as well. That wouldn't be a problem. But we would like to reserve those number, right? So can I call this two number a bit complement or something like that? This number, right? Like these two numbers. I can call them kind of complement of each other, right? I don't mean the complement in the traditional sense, but you get the idea, right? So that is what I'm trying to do here. Such complement such that we get the x, and the number of bits also is minimized. Because see, if we have extra bits, that is well and good, right? We don't have problem with that. But if we have extra bits, there is a number available which has a say 1 here also, which was not required. Maybe we can use it somewhere else, right? We can use it somewhere else because if we look at the number, so if we do XOR of this two, we get this number. Sorry, OR of this two, we get this number. So this bit is extra. So we can actually use a different number such that we don't have this bit already present in it. Maybe a number something like this, right? We can use it there. It will be better utilized there, and we can have the maximum play. So by this, we can already conclude that our best option would be to have the minimum number of bits in the second number or the permutation number, right? Such that we kind of those two should complement each other so that we can get x. There shouldn't be any extra bits. That would be our best approach. I hope that is up to this point is it's clear. Is it clear up to this point? Okay. So let's see what we can do after that. Once we have done this, we have concluded this. So what I'm going to do is I'm going to take the permutation, take the x, sorry, and if I do the XOR operator of it with I is basically the index. So what will it give me? It will give me those bits which are not present in X, right? Because remember that I have already mentioned that I is a number such that it has all the bits that X, its all bits are present in X. So what will it give me? It will give me those bits which are not present in X. So I'll get a number. Let's call it P. Now I can check for in a set, maybe in a map, whatever data structure you want to use. You can also use a vector with a boolean. That's totally up to you, and we can just get those values, right? If it is present, then we can just add it there, and whatever those values are left, there will be some values left, right? For example, our target is, let's say, 2, and at the first index we cannot do anything really in this first index. So maybe we will link 1 with 1, maybe we'll link 1 with 3, maybe we'll link it with 5, something like that, right? We'll have the number 5 on that index. We can do this kind of stuff. So that is what I've essentially done here. Let me just show you the code. So as I've already mentioned, this is I've just added all the numbers that will be required in a set so that I can access them much easier. You can use any other type of data structure as well. That's totally up to you how to implement it. And then this v vector is our final result. And then I've checked this condition. I've already explained it. Then what we are doing here is we are checking the condition of XOR, whether that number is available or not. That number isn't available, it will automatically go to s dot end. This is just the basic syntax of set only. So after that, if it is available, I'll just store it here and remove it from the set. So we don't accidentally end up using it later on. Although probably I don't think so we need it this line. But still I added it for safety. And then I've just outputted some whatever leftover values are there on the leftover indexes and output. Then there is just the value change. That's all there is to this implementation. I hope the explanation and the implementation part is clear. Is there any doubt? If there is any doubt, you can interrupt me in between. Okay, this question is, I would say, a very good question. I'd say, means there was a lot of observation in this question. So what this question is basically saying is that if we take an ith index and it is equal to the next index, and the next index is equal to its next index, kind of like 010 or 101010, then we can do a swap operation, which is basically swapping the second I plus 1 index and I plus 2 index. So essentially making 0102 0011 and 1010 to 110. These are the only two cases that can be possible, of course, because it's a binary string. So basically, what it is saying is, in plain language, is kind of, if you have a four-sized continuous alternating string in a binary string, then you can do the swapping of the middle two numbers. That's it's basically saying. And we are asked to how many total number of how many total number of combinations can we make of this string, so that new strings come up, right? For example, if we take an example, let's say this one is here, 1010. So how many combinations can exist? If you do the operation that was mentioned there, it will become something like this: 100, right? Yeah, just swap these two. So how many combinations were there? There were two in this case. So if you will notice something, which is that if there is an alternating pattern, and if there is not an alternating pattern, that's, let's say, there is zero, and this is basically what I'm trying to say is that this is continuous string. Okay, this part is an alternating pattern, and it is contained inside a non-alternating pattern. Okay, you will see here it is not alternating, so the case is not applicable to it. So if we perform the operation under any condition, let's say there is a string called AB, whereas A is just nothing but it's just the complement of B. Okay, that is what I'm trying to say. Yeah, it's an alternative pattern, and if I add a here, if I add a B here, and I perform the operation, so let's say in the second index with one base index. I'm talking everything in one base index. Okay, so it will become what? A B A B B. Yeah. A B B. So you can see that it is contained in itself only. Okay, it is not like influencing some other. For example, if I take here A again, so there would be a here as well. So you can see it is not influencing after the 3 bits. It is not influencing others, and it is not also influenced by others. What do I mean by that? Basically, it's not breaking the pattern. It is not dependent on something. If you consider a three basis, every three sets, it is not dependent, or it is making someone else dependent on it. So that does give us an edge. So I hope up to this part it's clear. And up to this part, is it clear? Uh, so we can see that only alternate patterns really matter to us. Okay, so it is not influencing something else if it is once it's contained inside a not non-alternating pattern. So what we can do essentially here is we can just separate out the alternating patterns, and then we can work on them. I've just taken an example here. Okay, this is an example. You can see this, there is an alternating pattern like this, and there is another alternating pattern like this. These two are not connected with each other because there is a 1 1. Okay, and there is a 1 1 starting as well. This is, by the way, an example also, if I'm not wrong. It's the third example, but I'm not sure. Okay, and this will not be 2 plus 1 plus 1. Okay, this will be 6. It does a mistake. I'm just not able to edit it. So if we do an operation at the very first index of the alternating pattern, I'm talking about this alternating pattern. Okay, if we do at the this is the original index, original string, and if we do an operation at the very first index, we can see that it essentially becomes this only 1 1 0 0 1 0, and then we can do an operation at 0, and then at 1, then at 0, and then at 1 at 0. We cannot do any further operations. So one thing you can notice here is that it's essentially dependent on the f minus 1 index and at the f minus 3 index. The sorry I plus 1, you can call I minus 1, or it's totally up to you. Uh, Basically, it's dependent upon the further 3 indexes and the next index if we are not doing an operation. You can see if we are not doing an operation, like in this case, it is dependent upon how many operations can we do in this remaining string, which is in this case is just one only, but it can obviously vary. And if we are not doing an operation in, let's say, we are not doing operation in this entire area, then it is dependent upon the third string. You can see it more clearly here as well. So if we are doing an operation, then it is dependent upon this string, which is the s plus I plus 3 index. Yeah. So since it is dependent upon only 2 indexes, if we are doing an operation upon this index and upon this index, we can clearly see it's kind of a dynamic programming approach, which would look something like this. Obviously, for a size of 1, 2, and 3, the answer will be 1, because we cannot do an operation. At least the minimum length should be 4. After that, once we have achieved the required length, at 4 it becomes 2, which is essentially nothing but the value at 3 plus the value at 1. At 5, it's nothing but value at 4 plus value at 2. So basically, it's a general formula comes up, which is value of n minus 1 plus value of n minus 3. As I've already told you that once we do an operation, the first 3 blocks gets cleared, right? We cannot assume it in the alternating index anymore. It changes completely. But at the same time, the rest of the part is totally unaffected. So that's why we have used this part. And if we don't use it, then we will consider whatever combinations we were able to make with the second index. So this is the dynamic programming part, and we have separated it using sliding window. We will be using sliding window to separate it and take out the length. Again, this is 6, this is not 4. And these are all the total possible combinations that can be made with a 6 length string, which is alternating. It is 6 in total. Okay, and we will obviously be multiplying this, because if it can assume 6 forms, it can assume 2 forms. We can obviously make a combination out of these two, which will be 6 into 2. This 2, which was also the answer. So now let's look at the implementation part. Okay, the logic is clear, or are there any doubts? All right. So here's the implementation. Um, this bit is just extra. I was just trying to derive a general formula. And make sure to change the mod. Okay, some people use a different mod. Generally, the mod is 10 to the power 9 plus 7. Make sure to change it to this. This is just a mistake many people make because we generally have this in our templates by default only. Okay, so I've just taken the inputs and then I've used a sliding window. I'm just counting if it's alternating, and as soon as it hits, if it is greater than equal to 4, I don't think so we required this line actually, as I've already stored in the dynamic programming part this values, but still I've added it nonetheless. And then we reset the value, and answer is multiplied by the dynamic programming dp of alter, whatever the length of the string is. And I've done the same thing here as well, just to make sure that if a string is ending at alternating, then in that case that else this else part will not be activated. So I'll just check it at the very end as well. And here's the part I explained you why it will be 1. Of course, the length is limited. We need at least 4 length here, and this is only 3 after 3. And after that, if we are not using that value, then we will be taking whatever the value it had when we didn't use it, the previous index. And if we used it, we have already seen that the alternating pattern goes away for the next 3 indexes. So we use the I minus 3 dp, and then we keep on adding it, and we do it up to 2 into 10 to the power 5, because there's 2 into 10 to the power 5. Yeah. So I hope the implementation part is also clear. Okay, thank you.